the eddy of turbulence, which is the equivalent of the rolling stone. This eddy is a rolling blob of water rolling in water. And then the second part will be meaning the second topic will be about the lifetime and then travel of a vehicle, which is the same as the animal. This thing, turbulence, people throw their arms in the air. Turbulence is a statement of admitting defeat. Imagine a jet that is discharged into a large pool, thing of water. In fact, this happens in every swimming pool. The water is being refreshed or replenished or heated or cooled by these jets that come out of the side of the pool. And the jet spreads predictably as a cone, meaning a region that's moving. But if you really pay attention, or if you do something nefarious inside the pool, you see a meandering kind of jet that fluctuates and that becomes thicker and travels like a wave forward. And that means this: if the jet has a speed v, then and the pool, of course, is stationary, the jet, in proceeding forward, is giving birth to eddies. And here they are. You don't see them, but the reason why they are these armpits is because they are inhabited by eddies that have to form because of the mover interacting what is not moving. And so this flow going downstream is a conglomerate of many small and few large, which altogether give the impression of a crazy moving thing, turbulent flow. And here is the, let's call it the elemental blob, which has a peripheral velocity clearly dictated by the way you discharge. So the peripheral velocity is v, and then the size of the eddy is d. And this blob is surrounded by water that's not moving at v because of the interaction with the slow surroundings. Everything else is not at this speed. So there is a friction between the blob and the surroundings. That friction retards, and the blob, it makes it slower and slower, to the point that as it travels downstream, the blob loses its identity. In other words, it becomes indistinguishable, meaning it dies, indistinguishable from the surroundings. So every eddy has a life travel and a lifetime. From here to death, the travel is called capital L, and the lifetime is little t. The same terminology as in the case of the rolling stone. I cannot resist. I have a story about Rolling Stones. It's not about the group, okay? By the way, you listen to Mary Hopkin?
Mary Hopkin?
Yeah, look, this is the greatest singer from the 60s, Welsh. Unbelievable. I think she still sings. Anyway, but Rolling Stones, yeah. So, when I was a junior at MIT, thank you, they just passed the requirement that these square heads called engineers had to take every year one course in the humanities. And Adrian enrolled in the course on psychology. And the course was being taught like a very famous professor, Teubner, another very brilliant man who ran away from the Nazis in the 30s because he was clairvoyant. That's what was still possible to run in the 30s. And Toimler was against students experimenting with LSD. LSD shows you how smart he was. But he decided to prove it. So he had a controlled experiment in which in one I don't know, glass booth or something, he had a student who was high, and then in the other one who was not, and then he would ask each the same question. And yes. And so the question was, what happens to a rolling stone? Yes. And the one who was high, he had to write it down. And he wrote it down. Do not throw rolling stones into a glass house because they gather no moss. That was the answer, you know. So the mind had made those two saying interbreed and gave this answer, which was nonsense. And this auditorium of 200 students just cracked up. There were many such examples. See that? So do not play with your brain, okay? Fine. So how do we predict the expected conclusion? That the bigger should travel farther and live longer. This way. So in the beginning, the blob has the kinetic energy of order. The mass of this blob is m. I'll write down immediately what that is. Kinetic energy of this order. This is rotational kinetic energy. Any rolling ball has more energy the bigger it is and the faster it rolls. And this thing has a mass which is of order rho and then d cubed. Write down because this is not very much. And then, and as I just said, because of friction with the immediate surroundings, this blob is being retarded by shear stresses that line the periphery. I call them tau, as I've done before. Tau. This shear stress is has to do with the fact inside the eddy there is shearing because in the center of the eddy there is no shear. So the order of magnitude of this tau, according to Newton's definition of viscosity, is mu, and then times v divided by d. Okay? I'm now writing on the blackboard all I know about mechanics. Kinetic energy, that's size, that's shear stress. If I integrate this tau over the surface of this ball, I get the friction force that retards the turning. So the friction force is tau times d squared. D squared is the scale of the surface of the sphere. And this is the friction force. Force times speed is power. So the power of this, meaning the work per unit time of dissipating this inventory of kinetic energy, I call it dissipation rate, is F times V. And then clearly the lifetime of the rolling and moving eddy, so this T is simply the ratio of the inventory of energy, KE, divided by the rate at which that energy is being dissipated, FV. And if you plug what I wrote here, KE on top, and then F from here and turn the crank, you obtain, in other words, you can do this on your own, you obtain d squared over nu. Nu is the kinematic viscosity defined as mu over rho. And the conclusion then is that yes, the bigger should live longer. In other words, lifetime, so bigger live longer in proportion with the length scale to power 2, which means in proportion with the body size m to power 2/3. So t should vary. This t does not vary. This is the lifetime of an object of this size. But in a population of diversity of sizes, now you're able to predict the existence of a diversity of lifetimes. Longer living, few, among many that live shorter lives. I'm talking about Eddies here, but those words apply to every diverse group of movers. All right, so that's about the lifetime. The life travel is obviously L is the same as V times T, that this L is V d squared over nu, obviously, because I multiply this by V. And once again, the bigger travel farther. So the bigger live longer and travel farther. Okay? And then finally, if you remember the lesson on the Rolling Stones, the real ones, every roll has its own time scale, like a ticking clock. So the time scale of one roll is obviously, you look at this ball turning, one complete roll has to do with this V, traveling, this arrow, a distance of order d. So that means d divided by v. And then the number of rolls is the lifetime, where is it? Here, t divided by t of one roll. And if you make the substitutions, you obtain dv over nu. And this group refers to the original identity of the eddy. Every eddy has a size and a rotational speed. And if you divide that product, v times d, by kinematic viscosity, every eddy has a Reynolds number. It's like saying my car is a model such and such Acura. That is the name, the brand of this particular eddy, one that's big enough and fast enough to have this Reynolds number. And d refers to the local dimension of the eddy, not to the dimension of the jet. V is also the speed of rotation of the eddy, not of anything else. And that is why this group is known, according to me, as the local Reynolds number. It has to do with the particular place in what is, of course, a very complicated flow field. Okay? So the conclusion is that the number of rolls of this eddy until death is dictated from its birth. So bigger roll, faster roll means more turns until disappearing. It turns out that the conclusion is even simpler. In another course called ME 532, it's called convection heat transfer. I teach that this particular number is a universal constant, no matter how diverse and complicated these things are. And that constant is of order 100. If this so-called Reynolds number is smaller than 100, you will not see an eddy. If it is big enough, such as 100, you see an eddy, and meaning you see the transition from laminar flow to turbulent flow. And once that number reaches 100, you see the birth of the eddies. And is the newborn that I'm discussing here, they're the ones that once born are swept downstream along with their neighbors, and again create a flow field that has been puzzling people until not only today but forever, because people who are raised with a notion that turbulence is a unexplained phenomenon, meaning they're educated to believe that, find it easier to create a career meaning their own career in turbulence, while proclaiming the impossibility of solving their own problem. You see, they're not the ones, meaning like Adrian, say, hey, listen, the problem is no longer an enigma. It's time to close the book and move on.